Now let's start. So why are we here? High performance computing. What is it? At some point when you're doing research in all kinds of domains, physics, chemistry, computer science, mathematics, um, you will come to a point where you have some really demanding scientific computational problems. So at this point, maybe your local hardware is not enough. For example, in your laptop or workstation, if you include your powerful GPU, maybe you have 1 teraflop, maybe 2 um, or less. And also for your storage, maybe it's not enough. You have a few terabytes of storage in your office. And then maybe you need more computational resources to tackle your computational problems. And therefore, you can come to us. We are operating our high-performance computing systems where we have a lot more resources and a lot more storage for even demanding projects. So as you see here, we have petaflops of computational resources and also petabytes of storage for also like big data projects. But keep in mind, it's not like magic systems, magic hardware. It's basically server grade hardware operated here at our compute center. So it's basically a lot more computational resources that you can use and all our users can use because all these systems are shared with all of the users of the system. We have multiple hundred of users. And that's also an advantage because if you are going to vacation, maybe your workstation in your office will be idling. But in our case, if you're not using the cluster, someone else will use the cluster and then can take advantage of these resources. So it's an efficient use of computational resources. So we are here at the Paderborn Center for Parallel Computing. We are a scientific institute founded beginning of the 90s, part of the Paderborn University. And we are a tier 3 and tier 2 cluster operator. Therefore, we have users from the state of NRW, but also all of Germany. We are part of some HPC alliances in Germany and NRW. So the NRW HPC NRW Alliance, and we are funded by the National High Performance Computing Alliance, the NHR. So what do? We operate our HPC systems for our users. We support our users with consultation and services and, for example, courses as this one. But we also research and develop new methods how to use these parallel compute systems efficiently and maybe also in new ways. Let's take a look at our available compute systems. We have 2 production systems right now, Noctua 2 and Otus. So Noctua 2 started in 2022, and our most recent system, Otus, started this year. And Noctua 2 is an Artus Bull Sequana system, while the new system is a Lenovo system. We can take a look. So they are conceptually similar. We have our racks of our server hardware here. It's running Linux operating system, and we have our nodes. In Noctua 2, we have 1000 nodes with AMD CPUs, and in total 140,000 cores. Each node has some memory. We also have nodes with even more memory. And we have a GPU partition with NVIDIA A100 GPUs, and we have an FPGA partition. And FPGAs are another kind of accelerator hardware that can be used to accelerate computations. So this is also a focus point of our research. This is why we have this FPGA installation with different kinds of these FPGA cards. And everything is connected via an InfiniBand, low latency, high bandwidth network. So these compute nodes, these servers are then connected also to the storage. So this is Noctua 2, and we will take a short look also on Otus, our most recent system. And as you see, it's also a bunch of racks with compute hardware. So in this case, it's from Lenovo. It's also using AMD CPUs. We have 684 nodes and over 130,000 cores. So these are more recent server CPUs with, and the nodes also have more memory. And also in the GPU partition, we have more recent NVIDIA H100 GPUs if you need them for your compute projects. So the FPGAs in Otus, we are still in the pilot phase where we figure out which FPGA acceleration cards to use in the cluster. And then we have faster InfiniBand network, and also the system has its own storage that is then connected to the compute nodes over the network. So the question is, what makes these computers HPC computers? Is it the architecture or how they are connected and so on? So high performance computing in general is the most efficient way to use computers to tackle the most computationally intensive problems. So they are basically a few aspects, I would say. One thing is that the hardware that you have, that you use it efficiently, that you program it efficiently to you get the most performance out of it. When the hardware is built, it has some specifications, how good it can perform. But if you program it, it doesn't mean you will reach this performance. You have to be clever about how you program it to make the best out of the available hardware. So this is one aspect for the efficient usage of the hardware. And the other aspect is then if you want to tackle really large computational projects, then you also would use the most advanced hardware that is available and that you can pay for, basically, to then also have the computational resources to tackle these problems. So, for example, if you have a certain problem that runs on your notebook, then this is fine. But maybe you will get to a more complicated problem, a larger parameter study where you need more computational resources. And even if you are really clever about programming your notebook, maybe just the available performance of your notebook is not enough, then you need more computational performance. Then you would need these server-grade server CPUs. And they are also different in comparison to your normal hardware in that there are a lot more cores. There are 192 cores in one node of the cluster on Otus. So, and there are 2 CPUs per node. So we have 96 cores per CPU. And also the operation is maybe different in that it is more efficient because the cooling is more efficient and how the power is provided to the system. Therefore, it's basically technically different in that the power and the cooling is more efficient because you need to be to it's also a cost factor for operation of these systems, and you have a lot of bunch of these server grade CPUs basically. And the if you just take one CPU core and compare it to maybe a gaming CPU core, then maybe the gaming CPU could be more performant because it can clock higher. But in our HPC cluster system, we just have a lot more resources. And another key aspect is parallelization. Therefore, you can save time and tackle larger problems by parallelizing your applications, your algorithms, to use a lot more resources in parallel, and therefore make use of all of this hardware. You're welcome. Okay, let's take a look at our application process. Because we are funded publicly, we also need to make sure that our resources are used efficiently, and for this we need to do a little bit of paperwork basically. So we will go through the steps of how to apply for a compute time project on our cluster systems. So the first step is to think about what resources do you need. If you have, for example, a parameter study, how many CPU core hours would your project run on the cluster? Now you have to do an estimation. And one example how to do an estimation is to run a little part of your complete project, for example, only one parameter combination, and see how long would it take. And or maybe if you have a simulation where you're simulating 10 nanoseconds of an atomistic simulation, maybe you can see how long would it take to only simulate 1 nanosecond. And then you will see how long will it run on a certain number of cores. For example, on 16 cores, it runs 1 hour. And then you can estimate, okay, how many core hours do I need to do the complete simulation of 10 nanoseconds, or how many CPU hours would I need to test or compute all of the parameter combinations for my parameter study. And then you will have an estimation of the resources that you need for your complete project, and also the storage that you need to store all of the input files and output files of your research. And this is also true for GPUs with the GPU hours, or FPGAs and FPGA hours. Second step is to look at the types of projects. So we have these different types. First type is test. This is just for 1 month, and the purpose is just to figure out if your software runs on our cluster and how to make it run more efficiently if this is a concern. So this is more important for software that is not so common, maybe your own software that you developed yourself. Then we have our small, starter, normal, and large projects, and here the differentiation is how many resources you get. So there are some limits. For example, for the normal project, it's up to 30 million CPU core hours, and for large is if you have more than or need more than 30 million CPU core hours. So these projects can also be multi-year projects if you wish so.
If I start, for example, with a starter, and I see, okay, that's not enough, and I want to switch to normal, how long or what would be the process there?
I think you would mainly need to do a new application. So we can you can get a little increase of your resources. Shin, how many percent of increase?
If I remember well, the exact number is 25%
Okay.
without extra reasoning, but more is also possible, I think. But you need to reason for.
necessarily use CPU, am I right?
So the question is, we are mainly using GPUs. Do you need CPU resources? No, because the GPUs are part of a node, and on the node there are also CPUs, and they are always also counted when you're running your compute jobs. Therefore, you will also need to think about how many CPU core hours you need.
So let's say I need more than 10,000 GPU hours, but I know it's maybe 3 million CPU. What should I do then? Still apply for the normal one, right?
Well, the normal goes up to 30 million CPU core hours, so that doesn't seem to be a problem.
But like, let's say I don't need 4 million. I'm not, I can estimate I'm below 4 million, let's say, but I mostly need
Well,
GPU.
it's not a problem. As long as you are in the limits of the project. I mean, there can be some little bit unforeseen things. You wouldn't try to get to the exact number in your application. You can, as long as you stay in these limits, it shouldn't be a problem for your application. So you decide for one of the types, and another different aspect of these types is in the next step, where you have to submit your proposal for the project in our submission system. You have to fill out some forms, who is responsible for the project, what software is used, and so on. And depending on the type of project, for the larger project, because you're applying for so many resources, then it also has to be a little bit more detailed, a little bit more detailed description of your project. And there's always a technical and evaluation, but you will this is quite fast, a few days, and then you can get access to the cluster. But the complete contingent that you apply for, the complete resources for the larger types of projects, you get after a few weeks, because there is an external review. So you already get access to the cluster, but you don't get all of the resources immediately, but after this review is done. And what you also get is an project short name. So this will be HPC minus PRF minus something. And under this project and project name, then you can run your compute jobs on the cluster. And you can log in, you get an account, and then you can also, as a project manager, add other people to the project. For example, your colleagues that also work on the same project need to do some computations, then they would also get an account and can also use these resources of your project to do some computations. Now, this was a short overview over the procedure, and we have more detailed information on our website with all the formal details. And in case if you have any questions or doubts, you can always just contact us, for example, via email on our support email, and then we can give you more information. Now, how to get access to the cluster and how does the cluster logically look like. Now, on this schematic, a small logical layout of the cluster, and we will start from the right side. So here you see all of the compute nodes. So every compute node has a name, and as explained, there are different types of compute nodes. For example, here on Otus, they then start with CN and then some number, or the GPU nodes start with the GPU and some number, FPGA nodes with FPGA and some number, and so on. And these are basically computers where your applications will run on. But you can't simply go to them immediately and just run some application, because this will end in chaos when every user just connects somewhere and just runs something. Therefore, we have our workload manager, the scheduler, that takes care of scheduling your compute jobs. So your compute job basically says, I need to run this application for 5 hours on one compute node, and this is the commands that run my application, and then the scheduler will check if there are free resources and then reserve the resources for you and run your application on the compute nodes. And if there are no free resources, then it will take a look when is the next time that there are some free resources that to run your compute jobs. And you talk to the scheduler on one of these login nodes. We have multiple ones, so the users can distribute on these nodes. You can connect there directly and then prepare your configuration files or input files, copy some files back and forth, and prepare your job scripts and talk to the scheduler, and then submit your jobs to the scheduler into the scheduling system. Yes, please.
What is the advantage of using multiple logins, like login 1, login 2?
Okay, why do we have multiple login nodes? Because we simply have so many users that one login node is not enough. Because people are working on there to copy some files back and forth and doing some configurations and preparing their projects basically, and therefore to just distribute the load of the users, we have multiple login nodes.
What I did, I accessed this computer with login 1, for example. I ran a training script. It was running in CPU. I was seeing that, for example, with top, right? You see the resources you use. Then I log out. I log in the login 2. I couldn't see the same scripts running in the login 2. I need to switch back again login 1 to see that these are running.
So the question is, if you run something in login 1, you don't see it on login 2. The reason for that is they are physically different computers. If you run it on one computer, it doesn't run on a different computer. So there was one thing we recommend to use this jump host to connect to these login nodes, and they distribute you to one of the login nodes. So there are also more intricacies to running something longer. So in general, the login nodes are not for running computations. They're just for preparing your computations, because if you run a real computation on a login node, it will be unusable for the other users, because it's then some CPU heavy work on these login nodes. So your real computations are to be run on compute nodes. And if you're running some computations on the login nodes, then it can also be aborted by us, because it's not the purpose of these login nodes. We will abort them and send you an email that you shouldn't do this because it bothers other users. And so the jump host, you first connect to there, and it will distribute you to one of the login nodes. And if you can also then over the jump host connect to the last connected login node if you have some tmux or screen session or something. Now, how would you connect to our cluster in general? You have to be in the university network. So if you're a local user at Paderborn University, if you're on campus, you're automatically in the university network over eDROM or over the wired network. If you are at home or at some other place and connect over the internet, then you need to use the VPN to connect the university network first, to then be able to connect to the cluster. For our training session today, we are going to use a special training node just for today for this course. So even if you are outside and connect over the internet, so you don't have to set up a VPN. But for our normal users, if you're outside, you always need to use the VPN. And then you're using SSH to get a command line on the front-end nodes. So let's take a look. For our course today, you first use SSH to connect to the training machine, and as we see here, SSH as an argument has the username or login name that you're using to connect at the host name. So this tells SSH to connect to this remote host and authenticate as this user. And for this course, if you are on the training node, then you can connect to the cluster by using SSH and then your username at fe.otus.bc2.uni-paderborn.de. And then you can do SSH otus, and then this sends you to one of the login nodes. And you can also use otus last to connect to the last login node that you've connected before. Or you can also do it in one step. So usually you only need to connect to the jump host in the frontend node if you are already in the university network. But for the training session today, you first have to go over the training node. So for some special cases, maybe where you need to connect directly to the login node, there's some more advanced SSH configuration, and you will find this in our documentation online.
Is it possible to collaborate actually with other universities? Let's say I have a project, I would like to invite another university to use also the resources. Is that possible?
So the question is if other universities can be invited for collaboration. Yes, this is possible because we have other users from other universities, our normal regular users. As explained, we have users from Paderborn University, from NRW, but also from complete Germany. It's just these your colleagues then have to apply for an account as is normal, and then they will get a login, and then they will be part of your compute time project. Yes.
So you have two SSH here. So based on what you said, the first one is like for the jump host, and the second one is for front-end nodes, probably.
Mm-hmm. Exactly.
Yeah. So why you couldn't implement it so like you handle it with just one SSH?
So in this case, this is to make it a little bit more convenient for the users to be distributed to some other front end. Like people would just take the first one, and everyone would be in the first one. So this, the second one is a special one that sends you to a random login node to distribute the users. If you need to, so you can also have it like in one step here, that is basically doing the same as above. But if you need to directly connect to one of a specific login node because there's still something running from you, then as explained, there's also some further documentation how to set it up with SSH to do it basically in one SSH.
This mainly for security reasons or convenience reasons?
Convenience reasons. Now on the cluster itself, there are different file storage systems for different purposes. And here is an overview over how this looks like. We have Noctua 2 and Otus, and we have this third storage system. And Noctua 2 and Otus have their own parallel file system. So this storage is directly connected to these compute nodes over the low latency, high bandwidth InfiniBand network to serve the data with this high bandwidth to serve all of the compute jobs. So as you see here, when one of the compute jobs would run off one of these nodes, then it would need to read some input files, so it has a better bandwidth, and the complete system has enough bandwidth for all of the users to this PFS. So this is the PFS of Otus, and Noctua 2 has its own PFS. And we have this other storage where your home and the PC2 data storage is located. Now the home folder, every user has its own home folder for some configuration files and so on. This is for everyone 20 gigabytes, and it's backuped. But for compute jobs, it may be not the fastest choice. It could be slow because it's not directly connected over this high bandwidth network. And as you see here, for example, PC2 users, user training 001 would be the path to the home folder. Then we have the data directory. You can find it for your project under the environment variable PC2 data, or here it's under PC2 groups and then the group name. And this is project specific. Therefore, it has the name of your project, as explained. In this case, it's HPC LCO user training for our training courses. But if you get your own compute time project, you have your project name. So the quota is depends on your project application, and the purpose here is final results and maybe programs that you're not changing, not modifying, and it is also backuped. And we have the PFS, and the purpose here is for storing files that are part of the computation, the input files, the output files. It's under /scratch /project name, and on the compute nodes, when your compute job is running, this would be the preferable storage to store your input files and output files. So the speed is fast because it's connected over the high bandwidth network. However, it has no backup. Therefore, once you have your valuable results computed, you maybe want them to copy over to the backup data directory. So there are different types of how to connect to the storage. CIFS or NFS network file systems or network file system protocols, and SCP rsync are different ways to communicate over SSH. So to connect to your home or PC2 data, you can easily also use SCP or rsync to copy some files there. To connect to the Perl file system, we recommend to use the network file system protocols, CIFS or NFS. You have to configure it a little bit into your operating system, but then you have basically, it's integrated in your operating system. For example, in Windows, it looks like a network drive, a folder that you can just copy some files over, and then they are sent over the network into the PFS folder. And this way, then you can also access some computational files, some results. We also have a Jupyter Hub. Right now, it's available for Noctua 2 users. We are still in the setup to set it up for Otus. And we want to also, we're in the process for an overhaul of the Noctua 2 Jupyter Hub to make it more reliable. So what is Jupyter Hub? Jupyter Hub is a web interface where you get an access to the cluster. You can launch a terminal, or you can edit some files or upload or download some files, but only for very small files. And you can run Jupyter Notebooks. So for some people, they prefer it to use these Jupyter Notebooks with these cells, with these programming commands.
Is it also project bound? So if I look in these resources I used.
So is the Jupyter project bound? It is basically just an interface for you that then also uses the resources of the cluster.
Can you go one slide back?
Yes, and it's also only accessible over the university network.
So you say that you use also similarity containers. In this case, what does it mean?
It's an option. I think Shim will talk about it later, about these singularity containers. It's similar to Docker containers where you can containerize some software and then run it or make it more portable. Yeah.
So I can create my own containers.
If you want. So if you have later on some questions, so in this course you can ask us anything, so that's why we're here. But later you can also find all the details in our documentation, doku.pc2.upv.de. And it's a wiki-like website with articles, with all the technical details, overview over the hardware of the cluster, and tutorials how to access it and what all of this means. Now, have you, at this point, I hope you were successful in connecting. Let's take a short look. So I'm also gonna connect to the training machine. So I'm gonna use user training 002. Okay. Here we go. Added my password, and now we are on the training machine. As you see here, I was on my local machine with my local username at the name of my local machine, and now I'm on the training machine with this login at training. So this way, in the prompt, you can always see under which context your commands are running. Now let's SSH into the jump host. So the first time that you connect somewhere, you will be asked about the fingerprint. You can say yes and do the password. And then we are on one of the login nodes. As you see here, for me it is login 3. And I'm in my home folder. And as we see here, this is the path to my home folder. And we can also go to the project folder on the PFS, on the Scratch. And there were already some folders. So you will get your project folder for your project, for you and your colleagues, the other members of your project. And there it's often a good idea if you have some configuration files, job files, and so on for your own, then it's convenient if every member just creates a folder for himself, for herself. And then inside of this folder, you can do whatever you want, have your own files, so you don't, it doesn't get so chaotic. And then you could also have, for example, another folder with shared input files. For example, if you're using the same simulation input files, or you can create here some folders and have some data that you maybe want to share with your colleagues. And you can basically use the normal Linux permission system to set up and control if your colleagues have access to the data or not. But else this project folder, it can only be accessed by the members of your project. Now, one of the tasks was to copy a file to the cluster, and I can do this. So now I'm here on, I have created a new terminal. I'm on my local computer, and I can create a file. And then I can use SCP to copy the file into my home folder. And for this, I can simply use the training machine. And here it's like SCP, then the file I want to copy, and then where do I want to copy it to? And in this case, it's you again see the similar argument as with SSH, the login name at the host name, but here we have additionally the colon and the dot. This means this is just a separator, and then comes the destination path on the remote host. And then it asks me again for the password. And if I go back to my home folder on the cluster, we see that here is the file with the typo that I just uploaded. And because the home folder is everywhere on each host on the compute cluster the same, we also find this file here again.
So it is the same when you do when you want to do copy from scratch as well, right?
So the scratch is not available on the training machine or the jump host, but it's available on the login node. So you would need to directly connect to the login node or use the CIFS NFS as documented in our documentation. Yeah, it's a little bit more complicated to set up, but then it's more convenient because then it's basically just part of your file manager of your workstation or whatever. This could be then more convenient if you like these kind of interfaces.